All right, ladies and gentlemen, today's class recording has started. So, in the last unit, we introduced the periodic table and what it told us. And so, let's see if I can remember how to do this. Yes. There. There it is. All right. And so, looking at the periodic table, let's take a look at chlorine, for example. All right. Chlorine is in bleach, so I suppose that's the best we can do at this point in time. Chlorine is a gas by itself, so it gets dissolved into stuff to make it bleach.
Pools too, right?
What?
It's in pools.
We do use it in pools, yeah. So as a way to kill bug or kill germs and that kind of stuff. So, but anyway, we talked about some different aspects of chlorine, and the aspect of chlorine that we focused most on in the last unit was the atomic number. And the atomic number told us what about chlorine? Number of protons, right? And also number of electrons. But there is another part of that atom, and that's the neutrons. And so, when we look at the neutrons, right, we know now that neutrons contribute what to an atom?
Nothing.
Mass. Protons contribute mass to an atom. They don't contribute what, though?
Energy. Positive or charge.
Charge, right? Neutrons don't contribute charge to the atom, but they do contribute mass. And we talked about that in the form of mass number being the number of protons and neutrons that are in the nucleus of an atom. And then that led us to isotopes, right? And we talked about isotopes being atoms that have the same number of protons but a different number of neutrons. They have the same atomic number but different mass numbers. Right? They're the same element, but they have a different mass, right? And that means they have a different mass number, right? So they have this Roman numeral 1, letter B, right? They have the same atomic number, but a different mass number. So there's a couple different ways you can fill in, like letter B, there's a couple different ways you could fill that in, right? They're the same element with a different mass number. They're the same element with a different mass. They're the same element with a different number of neutrons. Like any of those would be appropriate to fill into that space. As long as you understand this idea of isotopes, I really don't care especially what you write into that spot. So, because that's not the main focus of today's lesson, but we have to review that to get into what we're going to get into next. Okay? All right. Good with that so far? Okay. So last unit, we learned about the mass number. And hopefully remember, right? Mass number tells us what? The sum of the protons and the neutrons, right? Even though it has mass in the name, really it is a counting value, right? When we sum the number of protons and the number of neutrons, we're always going to get a whole number, right? We're always going to get an integer value because we're just adding, all right? However, and we just talked about this before, when you look at your periodic table, if you have the green one in front of you, right? Up at the top and kind of towards the left, it has a legend as far as what the squares in the periodic table tell you. And there are 4 things in each square, right? We know that the integer value in each square is the what? The whole number that shows up in each square is the what? That's the atomic number. And it just goes up by 1 as we move along the periodic table, right? Then we have this symbol, either 1 letter or 2 letters, right? Reminder, if you have a 2-letter symbol, the first letter is always capital, the second letter is always lowercase. I had to take off points on somebody's test in the last unit because they wrote 2 capital letters. So don't do that, okay? Then it has the name, right? And then that number at the bottom, first, it's not an integer value. And second, when you look at the little legend on your periodic table, what is the legend telling you that that number is? The atomic weight, all right? That's different than the mass number, okay? The atomic weight or the atomic mass, those two terms we use interchangeably, is a relative scale. Now, this is the third or fourth time we talked about a relative scale. What do relative scales do for us?
Compare.
They compare things. They are not measurements, they are comparisons. All right? If we are going to compare things, what do we have to do first? If we want to compare a bunch of values, or a bunch of anything, what do we have to do first? Collect data, yes. What are we comparing it to, right? What is our standard value that we are then comparing it to? So atomic mass, being a relative scale, a comparison for the mass of atoms, has to be based on something. And we base that something, or we base that comparison on the mass of a carbon-12 isotope. Okay? So let's talk about carbon-12 to refresh our memory, because we're going to do this a little bit more today. Okay? You should be able to tell me 3 things about an atom that is called carbon-12. Talk to the person next to you. What 3 things are you going to tell me about an atom that is called carbon-12? Discuss. Go.
Or 12. No. The mass number is 12.
Messed up.
Don't touch me.
Messed up, dude.
And you can tell it's carbon.
All right, so what 3 things can you tell me about a carbon-12 atom, or an atom that is called carbon-12? 3 things. What can you tell me about it? 6 protons, 6 electrons, and 6 neutrons. All right? Are we good with those 3 things? Good. All right. So we know it has those 3 things, but if we're going to use it to compare other things, we have to assign it a value. And so, as a basis of comparison for all the other atoms, we call we give carbon-12 a value of exactly 12 atomic mass units. Okay? So atomic mass is measured, and we should probably put measured in parentheses, or not parentheses, quotation marks, because remember, a relative scale doesn't actually measure things, it compares things. We compare these atoms through something called an atomic mass unit, or an AMU. And as a basis of comparison, we call the carbon-12 isotope exactly 12.000 atomic mass units. Jack, good.
My phone says 1201.
Okay.
Is there a point?
Now, the number on the periodic table is not an atomic mass. It's actually an average atomic mass. And we'll talk about what that is in just a second here, okay? That's actually the next section on this, okay?
Okay.
All right, so are we okay so far with this idea of atomic mass, right? And atomic weight is basically the same thing, okay? So atomic mass is a comparison, and we compare everything to a carbon-12 atom, okay? All right, next you have these 2 charts. Let's look at them separately from one another. So here's what I'm going to do. I am going to just focus on a certain portion of these charts right now. And those portions of the charts that we're going to look at are just these 2 sections right here. The one that says isotope name or isotope, and then the one that says atomic mass. Okay? So right now we're just focusing on these 2 columns. All right. We already established the fact that carbon-12 has 6 protons, 6 neutrons, and 6 electrons, right? So, maybe on the left-hand side, because you have a little bit of space on the left-hand side next to that chart there, figure out how many protons, neutrons, and electrons the 4 remaining isotopes that we have up here have in them. Use your periodic table, talk to the person next to you. How many protons, neutrons, and electrons do the rest of these isotopes have? Go. And those other 3 isotopes are isotopes of magnesium, so find magnesium on your periodic table. Okay.
Oh, wait, no, it's not the second test. I think that really but I think they might get taken away with 86% of the
All right. How'd we do? We okay with those? All right. All we've talked about so far is just mass numbers, right? We're dealing with whole numbers of protons, whole numbers of neutrons, whole numbers of electrons. So, but atomic mass isn't a counting thing. Atomic mass is a comparison thing. And we're always comparing it back to carbon-12. That's our standard. The one thing that makes this a little different is that when we talk about atomic mass and atomic mass units, our standard is not set at 1. It's set at 12. Okay? But that doesn't change how relative scales work. All right? For instance, here we have carbon-12, and here we have magnesium-24. Numerically, what are we seeing about the number of protons, neutrons, and electrons in magnesium-24 versus carbon-12?
Times 2.
Times 2, right? It's twice as big. But when we look at its atomic mass, is it exactly twice as big?
No.
If it was exactly twice as big, what would be its atomic mass?
24.
24 exactly. It's not 24 exactly. All right? What does that suggest about the nature of protons, neutrons, and electrons? Oh, good. They're not always exactly the same. Right? Because if they were, what would the atomic mass be? 24, but it's not. Right? It's close, but it's not exactly 24. Right? Same thing with carbon-13. Right? With carbon-13, we add 1 neutron, which is 1/12 of the nucleus, right? Yes? Does that make sense? When I say that, does that make sense? Okay. But does the atomic mass go up by 1/12? Is it exactly 13? Not exactly. It's close. It's not exactly 13, right? So we use this atomic mass value to compare the size of atoms to each other, all right? Anything greater than 12 means that it's bigger than a carbon-12 atom. Anything less than 12 means it's smaller than a carbon-12 atom. Okay? Jack, when you look on your periodic table, right, you told me that when you look at carbon, what does it say under carbon?
12.01.
12.01. That's pretty much what it says on all your guys, right? Yes? Okay. If we look under this atomic mass column, carbon-12 isn't 12.01. Carbon-13 isn't 12.01. So what is that number? Because it doesn't match anything that we have on this chart. All right? And the answer is it's an average. But what we find out, it's not just a straight up average, it's a weighted average. All right? Which seems difficult, but really it's not that bad. So, let's talk about that. Okay? We can put carbon-12 and carbon-13 and magnesium-24 and magnesium-25 and magnesium-26 up on the board. And all of those things exist out there, okay? But they don't always exist in a nice even distribution, okay? If we took a sample of carbon just out there in the real world, like coal from the ground, it's made of carbon, okay? If we took that sample of coal, we would find carbon-12s, and we would find carbon-13s, and we would find carbon-14s in that sample, but we wouldn't find an even number of 12s, 13s, and 14s. It's just not the way we find it. It's just not how it's out there in nature. So these isotopes exist, but not in the same proportions. Some exist more often than others. And so the average atomic mass, which is the number on your periodic table, not only takes into account what are those different isotopes, but it also takes into account how often they show up. Okay? How often they show up. So it takes into account the atomic mass of each isotope. How big is each isotope compared to carbon-12, but then also how often do each of those isotopes show up? Which ones show up more than other ones? If they do, they contribute more to the average. Okay? All right, do we have this written down? Come on, man. So, to talk about the weighted average, let's look at these two pictures that are on the back of your outline. Okay? Now, there's one thing I like about these pictures and one thing I don't like about these pictures, right? One, it demonstrates weighted averages really, really well, but two, it calls these numbers that are on these atoms atomic masses when really they're not. They're mass numbers, okay? But it still illustrates the point, okay? There are two isotopes of bromine that exist. Bromine 79 and bromine 81, okay? Find bromine on your periodic table. I'll give you a hint. It's over on the right-hand side, about halfway down. Find it?
35.
Okay. It's atomic number 35, right? Chris, for the discussion of our purposes, its atomic number is 35. What is its average atomic mass?
79.904.
79.904. Okay? So pretty close to 80. All right? If we look at this sample of bromine, bromine's a liquid, by the way, in its natural state. You can see that up on the board, too, that it's colored blue on that big periodic table. Okay? Blue ones are liquids. There's not too many liquids that exist out there, but there's a couple. Okay. Two. Right, two, yes. It's actually the big, bromine is actually the big one. It's like on the legend. That's just coincidence. Okay. But we have two isotopes of bromine, bromine 79 and bromine 81. Okay? If we were to take a sample of bromine, a little scoop of this big flask. And it was 8 atoms big. I know we could never take a sample that only has 8 atoms in it, but let's pretend. Okay? What we would find is that in that random sample, half of the bromine atoms that we would pull out of there would be bromine 81. Okay? They would have 35 protons, and they would have, if I can do this in my head, 46 neutrons, right? Okay? Half of those atoms would be bromine 79. They would still have 35 protons, but now they'd only have 44
No,
neutrons.
34.
34?
44.
No, 44.
79?
79 minus 35.
Oh, yeah. That was bad.
Sorry.
That was pretty bad.
So, if we took an average of those 8 protons, of those 8 bromine atoms, right? All we would do is we would take the 8 of them and add up the total, right? Then divide by 8, and we would get an average of 80. Are any of those atoms individually 80? No, but the average is 80, okay? Because we have evenly distributed the 79s and the 81s, okay? Tim, go ahead.
So there is no bromine 85,
Yeah, like those are the only 2 that we find naturally, right? So keep that in mind that we could make other isotopes of bromine if we want to, but here we're talking about stuff that we find in nature unaltered, that kind of thing. Does that make sense? Okay.
Yeah, I think we covered it.
Okay. All right, let's slide over to chlorine over on the right-hand side. So find chlorine on your periodic table. If you know where bromine is, chlorine should be pretty easy to find. Okay. All right. Chlorine also comes in 2 isotopes, chlorine 35 and chlorine 37. And if you remember the test that you took last week, there was a question about chlorine 35 and chlorine 37 on it, right? They're isotopes, and that means they're similar because they have the same number of protons, but a different number of neutrons, okay? So, chlorine is a gas, naturally. And so we have a sample of this gas inside of this container. It looks like a helium tank, but it has chlorine inside of it instead of helium tank. Don't breathe it in. That's not good for you. Okay. If we were to take a random sample of those chlorine atoms, again, 8 of them, we could never take 8 individual chlorine atoms, but let's say we could. We would find that there would be chlorine 35s and there would be chlorine 37s. But on average, of a random sample, 6 of the 8 chlorine atoms are chlorine 35. Only 2 of the 8 are chlorine 37. When we had the iodine, and we had an even distribution of 79 and 81, where was the average?
Right in the middle.
Right in the middle, right? But here, is the average of these 8 going to be 36? Nope. Because do we have an even number of 35s and 37s? 35s make up more of the sample, so they're going to contribute more to the average. If we add up all 8 of them, we get a total of 284. We divide by the 8 atoms, our average is only 35.5. That's how we get these decimal values on the periodic table, because we end up with one isotope being there more often than other isotopes, and that's how we get these weird decimals. Okay? Jack,
Yes.
the fact that carbon on the periodic table has an average of 12.01, what is that telling you about carbon 12 versus carbon 13? Which one shows up more often?
Carbon 12.
Carbon 12. Why? Because what's the average?
Closer to 12.
Really close to 12, right? Does that make sense? Okay. So that's how this weighted average thing works. So here's how we calculate it for any element. So we take the atomic mass of each isotope. I would give that to you. And then we would multiply that value by a fraction. That fraction being what we call the abundance over 100. Abundance is just the percentage that it shows up out there in the real world. All right? And so when we take the percentage over 100, we're basically just making a fraction, or like a decimal, right? And then that contributes, or that shows us what that element contributes, that tells us what that isotope contributes to the average. And then we add up all the contributions and we get the average atomic mass. Okay? So, let's do this. You guys have an example right there. It's chlorine, but let's do a different one. Let's flip it over to the front page.
Sulfur.
And let's take a look at these magnesium atoms. Okay? So, actually, yeah, let's do these magnesium atoms. Okay? All right, so here's our 3 magnesium atoms. Okay? And it has the atomic mass for all 3 of them. But in order to do this calculation, we not only need the atomic mass, we also need what percentage each of them shows up. Going back to the original chart, the next column on that chart, which you guys should be seeing, and I'm just getting is titled Natural Abundance, and it's a percentage. So we're going to figure out how much each one of these contributes to the overall average. All right, so starting off with magnesium 24. We take its atomic mass, 23.9850423. And then we multiply it by the percentage over 100. And if you know how math works, right? If we divide anything by 100, that's just the same as doing what? Moving the decimal, right, over 2 places, blah, 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 right? You can do that, that's perfectly fine, okay? So, let's run that through your calculator, and let's find out what we get, okay?
Chris, it's your race. Go. 18. Got it. Good.
Oh, I got it right. 18.
I got it for you. 18, but 9. Let me just look. You just sit there. Whoa.
I'm just going to take that to 4 decimal places just so I don't have to write down every single number. All right, good there? To find out the overall average, we now have to do that with magnesium 25 as well. So we take magnesium 25's atomic mass, right? How it individually compares to carbon 12. And then we multiply that by its percentage over 100.
It's 2.4985. It's 2.50. I would have 2.4985. No, 86. Oh, yeah.
I rounded it because
You didn't run the first one, though, did you?
No, I didn't actually, did I? So, I probably should actually. And then finally, right?
Good stuff. Wait.
because there are 3 isotopes, we have to do this calculation 3 times. All right, good with those 3? Does that make sense? And then, what do we do with these 3? Add them all up, right? So, add all 3 of these up.
Wait.
Okay?
Oh shoot, okay, I have it all ready to go. Oh, cool. Got it. 24.305. Yeah, I got it for you. Yes, I did.
You did.
Yeah. No, I
You
won.
did.
I won.
All right.
You have to divide that by 4.
No.
What do I with
No.
3?
No.
No?
So, don't do that, okay? Because doing the percentages takes care of the fact that magnesium 24 shows up way more than the other 2, okay? It's not a regular average, it's a weighted average, okay? And so we just add up all those different contributions. So, did we get it right?
Is the molar mass different?
Yes. Well, no, that's actually the same thing. We're going to talk about that tomorrow. So, okay. So, did we get it right? Where do we go to check if we got it right?
The periodic table.
Go to your periodic
Of
table.
course.
Find magnesium. What's the average atomic mass of magnesium?
24.3051.
Let's go.
All right. So, looks like we did pretty well. Okay.
How do they find the
And that
abundance?
is where all of those numbers on the periodic table come from. Okay? Now, tomorrow, we'll talk about what we use that number for, because it's more important than just figuring out the average atomic mass. Okay? So, for tonight, there are some problems from the book, but I also have a sheet that has some sample calculations, so if you want to try this a little bit more, you can do so. Answers, you know where you get the answers, go to the periodic table and find the answers, and that's where you'll get them from, okay? Tomorrow we'll get into using that average atomic mass to count atoms.